So for the benefit of our later viewing audience, this is CHEM100 Final Exam Review, Part 1. So we're going to share, and what I'm going to share is, where is it? It's taking me a second to find it. Let's see, I think it's this one. There it is. This is like a bank of questions that I might use to build a test, and I just compiled them all into a review. So this final review has a total of 200 questions in it, but I've only picked out about 60 of them. Some of them just take 5 seconds to get through. It's just memorization. Others are problems that we have to work through. So they vary in length and difficulty. In fact, the first set I picked out what I thought were the easy ones, and we'll just go through those first. And so I need to scroll down a little bit and I've tried to make them as big as possible so the resolution will be good for the recording. Okay, so here we have, scoot that over there. Here we have number 1. Let's see, before I forget, I better mark you present. Okay. So I'll check off number 1 and we'll take a look at this one. All right, water has a density of 1 gram per milliliter. Remember what density means is mass per unit volume. So water has is 1 gram for every milliliter. And the question is, which one of these objects will float in water? Right? So you need to know one other thing to tell if it's going to float. If the density of the object is greater than 1, since this is equal to 1, right, for water, then a density greater than 1 will sink, and a density less than 1 will float. So that's what we're looking for. We're doing those calculations to find out which one is equal to, greater than, or less than 1. And in this case, they're asking for which one is less than 1, which means it will float. So we look at object 1 and object 2 and object 3. Right? Now we can calculate these, right? 50 grams and 69.4 milliliters. We can do it that way and go all the way out to the end, calculate, but I'm going to show you a quicker way. Once you get this done, 60.9 grams per how many milliliters? 54.7. And the last one, 100 grams and 40 milliliters. 100 grams and 40 milliliters. Okay, all we need to know is the density is greater than or equal to or less than 1, right? And you can do that without your calculator, right? If the numerator and the denominator are equal, it's exactly 1. If the numerator is greater than the denominator, it's greater than 1. And conversely, if the denominator is greater than the numerator, then the density is less than 1. So we can say this is less than that, so that's less than 1. This is greater than that, so that's greater than 1. That's greater than that, so that's greater than 1. So without even having to get out your calculator, we can say object 1 answers that question. And of course, this is in the in my test bank, so it's got the answers marked already. But that's why 1 is the answer. And it didn't ask you for an exact value. It just said which one will float, which means that's all you have to determine. Okay. Let's see. I've got 2, 3, and 4 also. So let's go down to 2. Okay, 1.2 moles of oxygen atoms represent what? We have several choices here. And there's some formatting errors also. This little apostrophe here, that's supposed to be an X, a times. 0.7 times 10 to the 24th atoms. So when those problems crop up, I'll point them out. But you've got atoms, you got grams and atoms. So grams and atoms are 2 possibilities. So we need to do 2 types of calculations. Right? Since we already know the answers in atoms, we need to do the grams first, because if you're taking a test, the answer's not going to be there. So you got to do both. So how many grams would 1.2 moles of oxygen be? 1.2 moles. This is the problem in dimensional analysis. Conversion factors. Right? So how much does an oxygen atom weigh? We're not talking about the diatomic oxygen, which would happen if we were discussing chemical reactions. It would be O2. But oxygen atoms is just 16 grams for 1 mole. So if we resolve that figure, 16 and then times 1.2 is 19.2 grams. Okay. Now there are 19 atoms here, right? So don't be fooled. That says atoms, not grams, right? The number's right, but the units are wrong. So it's not D. It's not this one. That's 20 grams. That doesn't round up to 20. Okay. If it did, if it rounded up to 20, then it's a possible answer. But let's convert to atoms now. So 1.2 moles. And for this one, it doesn't matter if it's oxygen. An atom's an atom, and a mole is a mole, regardless of what it is. We just know the conversion factor is 6.022 times 10 to the 23rd atoms per mole. So 1.2 times that should be 1.2 enter 6.022 exponent 3. So I get 7.2 times 10 to the 23rd. Okay. Now that's scientific notation. If we convert it to exponential notation of any form we want, the purpose being to see if it matches anything that we've got in this. There's atoms here, 1.9, 10, that can't be. Right? 10 to the 23rd and 10 to the 1st, they're too far apart. But this one is pretty close, 10 to the 24th, and that is not scientific notation. But if we converted this one, what would it look like? If we made this 10 to the 24th, we would have to take 10 out of that one and put it over here. It's like extracting a power of 10 out of that And that would reduce this one to 0.72. Okay, so that's why A is the answer to this one. Well, that's a stubborn marker. Better mark them up as I go. 2. Now we're going to do 3. 1.8 kilograms contains this many grams. Okay, this one's fairly simple. Right? 1.8 kilograms. Now, I wrote it out. Well, the problem writes it out instead of abbreviating it. So how many grams is that? Well, the way I work with units of measure, if possible, and there's a prefix in here, and I know the value of the prefix, what does kilo mean? Kilo means 1,000. So that means 1,000 right there. So if it's going to be this, that, and that, then this is 1.8 times 10 to the third grams. Okay? Or if you wanted to go back the other direction, you say, all right, what does this mean? 1,000 grams is a kilogram. And there you go. So when it's in scientific notation, it's a pretty simple process. When it's in standard notation, then you have to deal with decimal movements. Okay, so the answer is A. And let's see, the next one I think is in sequence also, number 4. Then we start skipping. There we go. Okay, 13.4 grams of magnesium represents how many moles? Right, conversion. Again, 13.4 grams of magnesium, right? That's where we are, and here's where we want to go, moles, right? So our conversion factor has to give us moles and cancel grams. And remember, whenever you see grams and moles as a quotient like that, that's molar mass. So the molar mass of magnesium, let's get my periodic table here. Magnesium, we know where magnesium is, it's right over here. 24.31 grams per mole. So I divide 13.4 by 24.31. And I get 0.551, 0.551 moles. Okay, and that's taking into account significant figures too, right? Multiply, divide, you go to the least number. So let's see. Well, conversion factors don't count; they're exact numbers. But 3 here, 3 there. All right, now we go to number 8. Yeah, we'll come back to those others. The ones I just skipped over are in my difficult section. So we're going to take the easy ones first. Here we go, 8. Temperature conversion. All right. So we're going to convert 18.4 degrees Celsius to what? Well, see, we've got different choices. We've got Fahrenheit and Kelvin. So it's like that earlier problem. We've got to do both conversions to see which one's right. If we were to convert to Kelvin, that's the easiest one. Convert that to Kelvin, you add 273, right? That value for Kelvin is a negative, so that can't be it. All right, it's a positive. Positives and negatives don't meet. So we need to convert to Fahrenheit. Right, so what's the formula for conversion of Celsius to Fahrenheit? Right, I've memorized it a certain way. I always say it's Fahrenheit equals 9/5 Celsius plus 32. That just pops out of my head. Useful information that you will have available during the exam may give it a little bit different. It may say 1.8 here instead of 9/5. But I learned it back when fractions were popular. Okay, so we know this one, right? Plug it in there. It's already solved for the unknown. So we just leave it like it is, right? We put 18.4 right here, times 9/5 plus 32. Plus. So I get 65.1. Okay, that's A, I do believe. And it begins. Junk calls. Let me recondition my board for just a second. Take a minute. Maybe it'll erase easier if I do this. You might wonder what I'm putting on my board. It's WD-40. Works amazingly well. Okay, number 10. There we go. 2.93 moles of carbon dioxide at standard temperature and pressure will occupy what volume? All the volumes are in liter. This grams is ludicrous. It doesn't make a bit of sense. It doesn't occupy grams. It either is or isn't grams. So we can just focus on volume, right? So what do we know about this? If we know we have 2.93 moles of CO2 at standard temperature and pressure, does it matter that it's carbon dioxide? No, not to our gas laws. Our gas laws are independent of identity. As long as it's a gas, under standard temperature and pressure, we can do a calculation. So what is going to be a calculation? Well, we're not given a situation, remember, in gases before and after. This is the state. This is what it is right now. So that means the ideal gas equation. Okay. Now you have to remember, what is standard temperature and pressure for gases? Standard temperature is equal to 0 degrees Celsius, which is equal to 273 Kelvin. Okay, remember you have to have Kelvin here. What's R? Well, R is in useful information, and it's 0.08206 liter atmospheres per mole K. Okay, let's get this one, moles, 2.93 moles. Okay, we got that one. How about pressure? What's standard pressure? 1 atmosphere. There we go. We got everything except volume. So we're going to solve the equation for volume. So rather than write those numbers again in here, I'm just going to take them and stick them in there as I calculate. Well, pressure has to be moved over here, but it's 1, right? Divide by 1, like you can ignore that one. So we solve for this one, then it's nRT divided by 1. So let's see, 273, and multiply it by 0.08206, and then multiply it by 2.93. I get 65.6. Is that right? I check my decimal position. 65.6. Liters. And it's liters because of this right here. Okay. So the answer is B. Oh yeah, that erases a lot better. Put a little WD-40 on it. Okay, that was 10, now 13. Okay. All right, here, this one's a little bit tricky. 24.8 grams of oxygen. Right? It doesn't say oxygen atoms, it says oxygen. Right? When it says that, it means O2. That is where that will cause you to stumble. If you don't remember that oxygen is diatomic. Then it asks you how many atoms that is. Okay, so we're going to proceed with a chained conversion. That's all you have to do. You got to convert it to atoms some way. So we know that we have to get to numbers of stuff. And numbers relative to mass is molar mass. So we have this one, grams. What's the molar mass of O2? 32.00. Right? That gets rid of grams and leaves us with moles. Now, that's moles of O2. How many moles of oxygen atoms are there? Well, I'll tell you what, back up. It also gives you atoms, molecules, AMU. Okay, we have to do that calculation too. But at this point, we can find out how many oxygen molecules there are and compare it to B and see if that's right. Or compare it to B and D. So this one is 6.022 times 10 to the 23rd molecules per mole. Okay. So that'll give us the number of molecules of oxygen and see if that matches anything. Four point, that's 4.67 times 10 to the 23rd. Molecules of O2. Okay, 4.67, 10 to the 23rd, there's nothing there that matches. Right? So it's not molecules. While we've got molecules, how many atoms is that? Well, they're 2 to 1, right? So if we multiply this one, let's make room here for another. So this one is 2 atoms for each molecule. Okay, so now that's actually going to be 2 times 4.67, 9.33. Okay. Okay, that's why A is the answer. But I'm curious, how many AMUs do you have here? Well, the AMUs, if this is grams, pardon me for a second. I got to block somebody. I get junk calls. Every time I get a junk call, I run it through the de-spammer. There we go. Won't be hearing from them again. Okay, so atomic mass units. If you have a mole of oxygen, you will have 32 grams. If you have 1 atom of oxygen, you will have 16 atomic mass units. If you have 1 molecule, then you will have 32 atomic mass units. So if we have this many molecules, then that would be times molecules. So for every molecule that cancels this, you have 32 atomic mass units. It's the other way around. I'm sorry. It would be 32 atomic mass units over 1 molecule. Okay, so that's how you get to the number of atomic mass units. You have to know the number of molecules, and then each molecule is worth 32 atomic mass units. So you can tell right off that that value is going to be way bigger than 50. 50 atomic mass units would be something like let's see. Well, there's nothing exactly like it, unless I can look for a diatomic that weighs 24. No, nothing matches. Vanadium is 50.9. So nothing matches. That doesn't work. So we're left with A as the only answer. Okay, next one's going to be 18. Here we go. All right. 4 molecules of chlorine weighs what? All right, we're given 4 molecules of chlorine. How do we write chlorine? If it just says chlorine, remember that's one of those diatomics. So that's your starting point. Got to have that 2 there. So we have answers in terms of atomic mass units and in grams. So if we do atomic mass units, what does a chlorine molecule weigh? Well, I know 1 chlorine is the mass of one chlorine is 35.45 atomic mass units. So two of them is, let's see, this would be 90. This would be 70. 70.90 atomic mass units. That's for each. That's per atom and per molecule. So this needs to be times 4, correct? So that would be 3, and 4 times 7 is 28. 284, rounded off. Okay, that's why A is the answer. But if we were to calculate grams, how many grams would 4 molecules be? It'd be pretty small, right? So actually, we don't have to, because you know that it takes a mole of atoms to make 35.45 grams. And it takes a mole of molecules to make 70.9 grams. Yeah. So you know that these masses here, they don't even come close. We'd have high orders of powers of 10 to get there. So we really don't need to calculate it at all, for two reasons. One is those answers don't even come close, and the other is we already found the answer. All right. 27. I'm going to go skip down to 27 here. 27. There we go. All right. 9.4 milliseconds is equal to how many seconds? Okay, here's another one of those like that kilogram problem before. Let's see if we can do the same thing here. 9.4. Yeah, I can do better than that. Milliseconds. Right? And the prefix for milli is a small m. Right? What would a big M be? A big M is mega. Little m is milli. So what does milli mean? Milli means 1,000th of. So this right here means 10 to the minus 3. So now if we do that conversion, times 10 to the minus 3 seconds. Because this now is right here. And you're left with seconds. So that's why the answer is C. Okay? Also, there's that rule of thumb to check yourself as you go. If the unit of measure gets bigger, we're going from small millisecond unit to second unit. If the unit gets bigger, then the number has to get smaller. So it's kind of a check. If you came out with 9.4 times 10 to the third positive, you know you're wrong, because that got smaller, that got bigger, this has to get smaller. Okay, 27. Let's see what's next. 27, 28. Yep. Scroll down a little bit. 28. Let's see, I've got something blocking my vision. Let me move it. There we go. All right. 28. We're given 0.216 gram sample of sodium chloride. And it's given, the molar mass is given to you. You don't have to calculate it. And it's dissolved in enough water to make 5.2 milliliters of solution. Calculate the molarity. All right. So what do we need to know to calculate molarity? Molarity is equal to moles per unit volume. And this volume has to be in liters. So what do we need? Well, we need to know the moles of the solute, sodium chloride. And we need to know the volume in liters. So let's do the moles first. 0.216 grams. 0.216 grams. And we're going to convert it to moles. Right? Grams cancel with moles. So the value there is 58.44. So that would give us the number of moles we can plug in that position right there. $58.44. Okay, 3.6. I'm going to hang on to some decimal points here. 3.696 times 10 to the minus 3. That's so I don't encounter rounding errors. You know, keep a few extra decimals until the very end. And that works as long as you have multiply, divide only all the way through the calculation. All right, now we need to know volume. So the volume is given as 5.20 milliliters. Okay. So how many liters is that? Well, remember what milli means. Milli means 10 to the minus 3. There you go. 10 to the minus 3, 5.2 times 10 to the minus 3 liters. So if we plug this one in here and this one in there and divide. See, I've already got that one in my calculator. So I just need to put this one in. 5.2 exponent to the minus 3. And I get 0. Now we can round. 3 significant figures. 0.711. Molar. Okay? That's why A is the answer. Okay, let's check my position here. That's good. Okay, next 30. Scroll down to 30. All right. Notice we haven't talked a whole lot about nomenclature, because by this point, if you don't know how to name a compound, then you're lost everywhere else anyway. So there may be some compound naming, but it won't be a major part of either our study here or the exam. All right, a 116.9 gram sample of nitric acid solution that is 70% HNO3 by mass contains how many moles of HNO3? This is the dimensional analysis problem. All right, we're given 116.9 grams. 116.9 grams of solution. All right, but it's only 70% HNO3. Only 70%. I used to use 70% HNO3 in the lab, and that stuff is dangerous. It will eat the skin right off your hand. So we gloved up and clothed up, covered mask, and worked under the hood. So 70% by mass means what? 70% mass. That's what that means. That means that there are 70 grams of HNO3 for every 100 grams of solution. Okay? So all we have to do is multiply this times that, because this one's in the denominator, right? That cancels, and that leaves us with grams of nitric acid, HNO3. So 116.9, and then, well, you can multiply it by 0.7, right? 70 divided by 100 is 0.7. But you could do it this way also. 70 times and then divide by 100. Okay, 81.83. 81.83 grams of HN3. Right? Does that make sense? Well, yeah, if that's 0.7, then the answer should be about 3/4 of that value. So half of that would be 50, not quite 60, maybe 55. And then another half of that would be about 8. Yeah. Okay, we're close. I like to do estimations like that. It keeps my mind active and keeps me out of trouble too. Spot your own mistakes. Okay, but the question is, how many moles is that? Okay, so we need to know the molar mass of HNO3. All right, we're going to have to calculate that. So hydrogen. Hydrogen is 1.01. Nitrogen is 14.01, I believe. Yep. And 3 oxygens, 16 each. There we go. So what is that value? 1.01, 14.01 added, and then 16 3 times. So I get 63.02. 63.02 grams per mole. So we divide 6302 into 8183. And just so happens that they're in the proper order in my calculator. I can just hit the divide button. 4 significant figures. 1.298. Moles. All right. All right, they rounded off to 3 significant figures. That's wrong. You got room for 4 significant figures. I wouldn't throw any of them away. Well, it's the best answer. Remember what I say about multiple choice? It's not the exact answer. I guess technically you could say none of these, correct? Because you're allowed 4 significant figures. That's an exact number. All the way down. I'd still choose 1.3. It's a better answer than none of these. 31's next. So let's scroll that one in. Let's reposition. That's good. Okay, 31. Now we have a 12.0 gram sample of helium gas. Okay, looks like we're headed for a gas law problem. Occupies a volume of 14.4 liters at a certain temperature and pressure. Right? It doesn't even tell you what the temperature and pressure is. What volume does a 24 gram sample of neon occupy at these conditions of temperature and pressure? Okay. So you actually have 2 different samples, a 12 gram and a 24 gram. Right, so you got a volume here with 12 grams of helium, And you've got one over here, not to mean that they're the same volume, I'm just saying that's where it's located. You have a 24 gram sample of neon. Okay, at a certain temperature. So they're both temperatures are the same and pressures are the same. All right. So what could possibly be the variable here? Well, two variables actually, moles and volume. All right. So we need to compare the moles. How many moles is 12 grams of helium? Right. Well, let's look at the molar mass. Right. 1 mole of helium is about 4 grams. So this is 3 moles, correct? How about neon? How much does neon? Neon is 20.2. Right? So 20 into 24 is what? It's just a little over a mole. Right? It's a little bit more than a mole. Not much, a little bit more. Okay. So much for the thinking part. Now we have to do the calculation. Right? We can't logic this one out. We have to actually do the calculation. So, which law is going to apply here? Avogadro's law. Avogadro's law says if these two are constant, then this one divided by that one is equal to this one divided by that one. Okay? So, what's the volume here? 14.4 liters. So this is 14.4 liters. There. How many moles is it? Well, it's 3 moles. How about this one? Well, the question is, what's the volume? Right? So the volume is unknown. How many moles do you have? Well, now we can't go with just greater than 1. We have to actually calculate it. So this number of moles is going to be 24.0 grams divided by 20.18 grams per mole. Okay. So this one, I'm going to do that calculation first. 24 divided by 20.18. Right? So that's 1.189 moles. Now this one, to solve for that one, this one has to come over here. So this one is going to be multiplied by 14.4 and then divided by 3. So I get 5.71. Okay, that's why the answer is A. So that was an exercise in Avogadro's law. Now, what if you don't remember what to call it? Well, remember, PV11 over NT equals P2V2 over N2T2. Remember the combined gas law. So in this case, if pressure and temperature are held constant as they were, just cover this one up. Just a second. Hello? Yes, ma'am. I'll be there. You too. Bye-bye. Always answer the doctors. Okay, so if these are constant, then they drop out, and the only thing you've got left is volume and moles. So you really don't have to remember Avogadro's for this problem. You know, if another question pops up and says, which one of these is Avogadro's law, then, you know, you're stuck. You got to know it. But to answer this question, all you have to know is the combined gas law and how to manipulate it. Let's see, that was 31. Let's skip down to 34. We're still in the easy group. All right. A 16.4 liter sample of gas at STP is heated to 55 degrees at 605 torr. What's the new volume? Notice that you're given the starting conditions, 16.4 liters at standard temperature and pressure. And then it's the temperature and the pressure are changed. So this is a before and after problem. Right? So we can go right back to the combined gas law. Okay, now what has not changed in all of this process? Moles, right? The gas is confined. We didn't add moles. We didn't subtract moles. So this term drops out. Now all you have is P1V1 over T1 equals P2V2 over T2. You just have to be sure that you put them in the right place. What's the P1? Well, standard pressure, 1 atmosphere. What's the V1? Well, the initial volume is 16.4 liters. What's the initial temperature? The initial temperature is 0 degrees Celsius, which is 273 K. Okay. Now you're going to a new pressure, but the pressure is in torr. You need atmospheres. So how do you convert torr to atmospheres? You just divide by 760. 605 torr, right? Torr here and atmosphere here. Right? That's why you divide by 760. So in this pressure, we're going to have 605, right? Yep. Divided by 760. And that's atmospheres. 1 second. Come on. Come on. Wow. So the question is, what's the new volume, which is V2? So that's our unknown. How about temperature? The new temperature is 55 degrees Celsius, which is what in Kelvin? Well, it's 55 plus 273. There you go. So now all we have to do is solve the problem, solve the mathematical, right, for this one. So we can say this one divided by that one is this term, 16.4 divided by 273 is over here. Now we're going to multiply it by this one, 55 plus 273. So I have to add those together first, which is 328. And then I multiply it by what I had over here. And then this one has to come over here in the denominator, right? It's numerator over here, denominator over here. So this one is going to divide into that one. So 605 divided by 760. And then it's going to divide into everything I've got so far. So now I've got 24.7. Yeah, 3 significant figures. 24.7 liters. So V2, 24.7 liters. Rounding error. Right? Best answer, 24.8. I don't know why that was rounded off. Oh, they're right. 24.8. My fault. Because the next number to the right of the 7 was a 5. So it needs to be rounded up. Okay, that was 34. Now we're going to 38. Here we go. Okay. Looks like we're going to get into some balancing equations and stoichiometry. Okay. There we go. All right, 38. A 3.1 mole sample of, what is that? Potassium chlorate, right? That's a polyatomic ion right there. The chlorate ion, potassium chlorate, was decomposed according to this equation. And it's even balanced for you, right? 2 potassium, 2 potassium, 2 chlorine, 2 chlorine, 6 oxygen, 6 oxygen. It's balanced. How many moles of O2 are formed, assuming 100% yield? Okay. So we're working from this balanced equation to potassium chlorate yields 2 potassium chloride plus 3 oxygen. Okay. And we're given what? 3.1 mole sample of this. And the question is, how many moles of O2? Right? So that's the unknown. What can we do with that? Right? It's already in moles. Right? And I've always said, you can't go anywhere in a balanced equation unless you have moles. Right? If you've got volume, you're stuck. If you've got mass, you're stuck. If you've got concentration and volume and whatever, you're stuck. You've got to have moles. We've already got moles. So now we can convert from that to that. So what is the conversion factor? 3.1 moles of potassium chlorate need to be converted to that many moles of oxygen. So moles of oxygen ratioed to moles of potassium chlorate. What's the ratio? The coefficients are always the ratio for this conversion factor. So you have 2 here and 3 there. So 3/2 of 3.1 will give us our answer. I get 4.7 because we only got 2 significant figures here, right? 4.7. There you go. 4.7. And it was 38. All right, 38, and now we're going to 52. Going to be a big jump. 52. Here we go. All right, these are going to be quick answers. A blank change involves a change in one or more physical properties, but no change in the fundamental components that make up the substance. All right, so what kind of change is that? Well, the giveaway is here. Physical properties. Without changing the identity of the substance, that's a physical change. That's the only possibility. So that was 52. How about 53? A blank change involves a change in the fundamental components of a substance. A given substance changes into a different substance. That's a chemical change. Another way to say it is the identity of the substance changed. Right? If it's going from potassium chlorate, is a substance. If it changes into potassium chloride and oxygen, those are two different substances with different identities. Okay, 54. Got this one on my list too. A blank is a summary of observed behavior, and a blank is an explanation of behavior. All right, that is the difference between law and theory. A law is a summary of observed behaviors. It may just say something like Newton's first law of motion. An object in motion tends to stay in motion unless acted upon by an external force, or an object at rest tends to stay at rest unless acted upon by an external force. That's a simple summary of observed behavior. Or Newton's second law, which says a mass acted upon by a force, an unbalanced force, will produce an acceleration. And it usually looks like this. That's a mathematical summary of observed behavior. Okay? That's a law. Doesn't explain why. Doesn't say anything about why it's doing that. That is reserved for theory. Here. A theory is an explanation of behavior. When you can get it, a theory is better. The reason being that with a theory, if you tweak one of the parameters of a theory, you might get a different behavior. But if you tweak one of the behavior parameters for a law, you still get the same law. It doesn't change. So you can go farther afield with theories than you can with laws. Okay, 61's next on my list. The hit parade. 61. Okay, I'll write this one up here. Okay, a certain isotope, X, with a charge, 2 plus charge. Okay, remember the positions around the symbol. That's charge, that's number of atoms. This is mass number, and this would be atomic number. Okay, so this isotope, which is what? Well, when we say isotope, now we're specifying the number of neutrons, which we do. It has 37 electrons. 37 electrons and 73 neutrons. What's the mass number? So what do we need for the mass number? Well, the mass number designated A, right? This is A and this is Z. So A has to be Z plus the number of neutrons. All right, we got the number of neutrons, 73. What we need is the number of protons, the Z number. Well, if you've got 37 electrons, and remember how a charge is developed on an atom. It's the balance between protons and electrons. And the only way you can change that balance is by adding or subtracting electrons. You can't touch the protons. So if this were neutral, how many electrons would you have? Well, if you add 2 more electrons, then you cancel out those 2 pluses, right? So plus 2 electrons equals 39 electrons for the neutral atom, which also means 39 protons. So this is 39, this is 73, and that's equal to 112. Mass number. There it is right there. Okay? I'm starting to lose my WD-40. Let's see if there's some left on this rag. See if that works. 61, next is 64. There we go. 64. A chunk of sulfur has a volume of 5.95 cubic centimeters. So we've got sulfur, and its volume is 5.95 cubic centimeters. What's the mass of this sulfur? If the density is given, 2.07 grams per cubic centimeter. So the density is 2.07 grams per cubic centimeter, right? Will that sink or float? It's going to sink right to the bottom of water. You put this in water. Actually, if you put that in water, it'll react, but slowly. Anyway, so this is equal to mass divided by volume. So we've got volume right here, right? 5.95. We just solved for mass. So that means this times that equals the mass, right? It's a simple calculation. As long as you start from the correct formula, D equals mass divided by volume, then you can arrive at the correct answer. Let's see, 3 significant figures. 12.3 grams. Okay, and there's your answer. All right, moving on. 69. There we go. A compound contains an unknown ion, X, and has the formula X dichloride. So X and 2 chlorines. And it says it's an ion. This is an ionic compound. So we can say something about the charge, can't we? Chlorine's always -1. So X has to be +2. Right? So we know that. Now we know ion X contains 20 electrons. So this ion has 20 electrons, correct? So how many protons does it have? Well, if we add 2 electrons to balance that out, that'll give us the number of protons, because in a neutral atom, the number of electrons and the number of protons have to be equal. So if we add 2, then that implies 22 protons. So the question is, what's the identity of X? Well, now that we know the atomic number, all we got to do is go to that periodic table, right? Look for 22. Let's see. Where's 22? Let's move over here. There we go. And let's see. Titanium. So we have titanium with 22 protons. Well, it's also still has a charge, correct? We identified X. We identified the element of X, but we didn't add, I didn't add the charge, right? It's still an ion. We didn't make it neutral. We used neutrality to determine the atomic number. So the answer is A. Let's see, scroll down. 76. Trombones. Here we go. I don't even have to write this one up. This is a matter of identity. 1 cubic centimeter is equal to what? It's equal to 1 milliliter. They're exactly the same measure. Well, we know it's not a liter. We know it's not a deciliter. We know it's not a centimeter because it's cubed, right? And we know it's not a millimeter because also it's cubed, plus it's the wrong unit. So the only answer that comes even close is the milliliter, because this is an expression of volume and that's a volume. So what is a deciliter? I'm just curious. A deciliter. A deciliter is a tenth of a liter, correct? So this would be 0.1 liters. A deciliter. How many milliliters is that? Right? 3 places, 100 milliliters. So that would be equal to 100 cubic centimeters. Right? That deciliter is too big to be a cubic centimeter by 100 times. All right, that was 76. Now let's jump down to 90. Oops, come on. There we go. 90. One more. There it is. Okay. What time is it? Got till 11:50. You know, we might get finished with this today. Yeah, if we keep it up this rate. Okay. A graduated cylinder contains 20 milliliters of water. Sometimes it helps draw a picture. Graduated cylinder contains, let's say, if this is a 50 milliliter, it would be about right here, right? 20 milliliters, 20.0 milliliters of water. Okay? An irregularly shaped object is placed in the cylinder and the water level rises to 31.2 milliliters. So it's going to go up to 31.2 with this object in the bottom. Okay? If the object has a mass of 80.4 grams, what's the density? All right, remember what we need for density. Mass per unit volume. And look at the answers. Grams per milliliter, right? All of them. So you know what your volume units need to be. Milliliters, that's good. And grams you're given as 80.4. 80.4 grams. Now we have to find out the volume of the object. So what is the volume of that object? Well, it's the difference between the volume before and after, right? You put that object in there, why did the water rise? Because that object displaced some of the water. And it displaced how much? Right? 11.2, correct? 31.2 minus 20 equals 2.11. Right? And we can keep all of it. Right? Because the decimal's here, we can keep 11.2 milliliters. Now that calculation has 3 significant figures. So 80.4 divided by 11.2 is 7.18 grams per milliliter. Right? The real trick to answering this one after you've identified the formula is how do you find the volume of the object? This is the best way to find the volume of an irregular object is to drop it into some liquid and measure the displacement. Of course, you want to choose a liquid in which the object is inert, right? As a lot of solid objects are inert in water, so water is a good choice. But if you had an irregular chunk of sodium, you wouldn't want to drop it in water. You'd have a nice little fireworks. So you'd instead of water, you'd put oil in there, It won't react with oil. And measure the difference. Okay, 91. Just scroll down for one. Oh, okay, definition. All right, 91. Homogeneous mixture is also called a solution. Right? That's just a fact. Homogeneous mixture, we know what a homogeneous mixture is. All the components in the mixture are evenly distributed so that any sample you take anywhere has exactly the same composition. And that's true for solutions. All right, so 91 is D. We'll go down to 94 for the next one. Oh, another definition. A mixture of sand and water is what? Well, a mixture of sand and water, as opposed to homogeneous, it's heterogeneous, right? And there's nothing there for it. Solution, solvent, solute, aqueous solution. No, there's no mention there of heterogeneous of any kind. So that's why the answer is none of these. All right, big skip. We're going down to 113. There it is. All right. Definition again. A solution can be distinguished from a compound by its what? A solution can be distinguished from a compound by what? Well, let's look. Let's find the best answer. Color has nothing to do with it. You can have colored solids, but you can have colored compounds, and you can have colored. Heterogeneous nature of a solution, the compound and the solution are both homogeneous in their own way. A solution is homogeneous by the mixture of solute and solvent, is always constant. A compound is homogeneous in that it has exactly the same mass ratio of every element in the compound. No matter what its source, it's always the same. That's the law of definite proportions. So a solution can be distinguished from a compound by its variable composition. You know, I don't think this is a good question. Neither one of them have variable composition. Oh, well, if I stretch the meaning, a solution may have a different composition than a compound. But when you're talking about composition of a solution versus composition of a compound, you're actually comparing apples and oranges. Right? So that's a bad question. I shouldn't have picked that one at all. Let's throw 113 out. Never do that one again unless I change the answers to make more sense. How about 123? Let's see if it's any better. Okay. We're getting into pH now. Getting into acids and bases. So, 123. So a solution where hydrogen ion concentration is equal to 10 to the minus 13 molar is what? It's either basic, neutral, acidic, strongly acid, or two of the above. Well, let's see. Is it acid or base? That'd be a good place to start. It's not neutral, right? Neutral would be what? 10 to the minus 7 molar equals neutral. So that's actually our reference point. If the concentration of hydrogen ions is less than neutral, it's basic. And if it's greater than neutral, it's acidic. Why is that? That's because of this equilibrium. 10 to the minus 14. Okay? That's always the case in water. So if this is 10 to the minus 13, what is the hydroxyl? That's 10 to the minus 1. 10 to the minus 1 is way bigger than 10 to the minus 7, so you know it's got a lot of hydroxyl in it, which means it's basic. Right? So we just answered our question. That's a basic solution. All right. Next, that was 123. Yep. 124. We just scroll down a little bit. A solution with a pH of 2 is how many times more acidic than a solution with a pH of 6. So we have a pH of 2 and a pH of 6. First of all, is that a correct assumption? The pH of 2 is so many times more acidic than pH of 6. Well, yeah. The nature of the logarithmic transformation plus the negative sign those combination means that the higher acidic content of your sample will come with a lower pH value. You also have to remember that the pH scale is logarithmic, and this is common log, base 10. That means for every 1 pH unit, you actually change the value of hydrogen ions by 10, a factor of 10. So how many factors do we go here? Well, 2 to 3 to 4 to 5 to 6, 4 times. So this would be 10 times, this would be 100 times, this would be 1,000 times, this would be 10,000 times. Right? So 10,000 times is the difference right there. Or we could say 10 to the 4th power. It gives you the same answer. All right. 128 is next on my list. Okay. Oh, this is a significant figure problem. Okay, what are we given? Well, let's see. A student finds that the weight of an empty beaker is 14.049 grams. So the empty beaker is equal to 14.049 grams. Then she places some solid in the beaker, and the combined mass is 14.12 grams. So beaker plus solid is equal to 14.142 grams. How many significant figures is the mass of the solid? Well, first of all, how do you find the mass of the solid? By difference, right? If this is the weight before and this is the weight after, how did it get that weight? Well, the only way is by the solid. So if you subtract the initial from the final, you'll find out the mass of the solid. But we also want to know how many significant figures are we allowed to keep. Okay, so we take this one and we subtract 14.049. Right? So which significant figure rule is this? Add, subtract. Right? Not multiply, divide. Add, subtract. So first we start off and just keep all our decimals, and then we decide how many we can keep afterwards. So 9 from 12 is 3. And then 4 from 13 is 9. And 0 from 0 is 0. Placeholder. Right? Right, no orphan 0 decimals here. That decimal stuck out here by itself, it gets a bracketed 0. Right? We don't start a number with point. We start it with 0 point. Okay, how many significant figures can we keep? Well, both of these come out to the third place. So we can keep the last one, which means non-significant here, right? 2 significant figures. Right? That's why the answer is A. All right, 128, let's see. 129, let's scroll down just a little bit. Definition time. (129) A substance, when dissolved in water, produces a solution that conducts electric current very efficiently. Okay, there are a lot of indicators in that sentence. First, the substance is dissolved in water. And when you do that, it will conduct electricity. Right? So by definition, that has to be an electrolyte. Why? Because it dissociates into individual ions that are now able to carry a charge from one of the electrodes to the other. So that's an electrolyte. But then the next piece of information tells us whether it's a weak or a strong. It conducts electric current very efficiently. That means that it's a strong electrolyte. Okay, so that's why we've got A for our answer there. Okay. All right. 141 is next. Right here. Oh, we do have a naming. Okay. An aqueous solution of HF would be named what? Well, if you just have the compound, HF is like this, and it's a gas. So we would name that hydrogen fluoride. Fluoride. Now, why am I doing this? Because our acid names are based upon the compound name. When we put it in water, now it becomes an acid, and we have to use acid naming convention. So first rule, is there any oxygen there? No, no oxygen in that compound. That means we proceed the name. The name is preceded by hydro. And then you take, that takes care of the protons. Then you take this part of the name, and what is it called? Fluoride. Ides become X. So it's hydrofluoric acid. Okay? All right. Moving on. Uh, 143. Oh, this one's going to take a little bit of work, right? 143. Actually, this one should have been in my moderate list, but this is the last one in the easy list, so it's a segue into the moderate list. An aqueous solution of ammonium sulfate reacts with an aqueous solution of barium nitrate. So those are your two reactants. You got to write ammonium sulfate. Ammonium is that with a +1 charge. And then sulfate is this with a 2- charge. All right? So we have to balance our charges. We need 2 of these, correct? 2. And then barium nitrate. So barium is an alkaline earth with a 2+ charge. Nitrate is a polyatomic ion with a -1 charge, and we need 2 of them. Okay? So what type of reaction is this? This is the one type of reaction where it's easy to determine the products. It's just a double replacement. This cation goes over here and replaces that cation. So now we have ammonium nitrate. Right? +1, -1. And then we have barium sulfate. Barium sulfate. These are both 2 minus, 2 plus. They 1, 1. The question is, what is there a solid here? Do we get a solid out of this reaction? Well, you might remember that all nitrates are soluble. Actually, all ammonia compounds are soluble too. Ammonium. So that one is aqueous. Barium sulfate, you might have to look that up. A useful information table for solubility of various compounds. Remember the one with cations across the top and anions down the side, and you just follow them until they meet. And what is the square clear or grayed out? If it's grayed out, then they make a solid. Well, if you follow those and do that, you find that this one is a solid. In fact, the formation of that solid is what drives the reaction. If you put 2 of these together and you got aqueous solutions on the end, there's effectively no reaction, right? There's no change. These are individual ions in solution anyway. Ammonium ions, sulfate ions, barium ions, nitrate ions in solution. So the only way you can get a reaction is for a cation and an anion to get together and do something different. Either make a solid or, in rare cases, make a pure liquid that separates, or make a gas. Sometimes they make a gas. And that would drive the reaction. But if they're all aqueous before and after, you got no reaction. All right, so the answer to this one is A, barium sulfate. All right, let's see, 143. Okay, now I'm into the moderates. Got to go back up to 46. So let me scroll it. Oh, that's going to take forever. Let's go over here and use this sidebar. Oop, too far. There we go. 46. Let's see. I didn't mean to mark that one out. Just wanted to check it off. Check off. 46. There we go. Okay, a 50.93 gram sample of barium hydroxide is dissolved in enough water to make 1.2 liters of solution. Okay, how many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? All right, this is a 2-step problem. First of all, you're going to make what's called a stock solution out of this much barium hydroxide in that much water. And then we're going to take that, and that's based upon molarity equals moles divided by volume. Then the second step is we're going to do a dilution problem. Once we know the concentration of our stock solution, then we can use a dilution formula to answer the second part. So this is a 2-part problem. All right, we're starting off with 50.93 grams. All right, what do we need for molarity? Got to have moles, right? So 50.93 grams of barium hydroxide is how many moles? We need the molar mass of barium hydroxide. Okay, so what's barium? Well, let me see. I'm going to look at my chart up on the wall. Oh, can't see that far. I got to get this one. Barium, 137.33. Then 2 oxygens, 16 each is 32. And 2 hydrogens, 1.01 each is 2.02. There we go. Now we add those together. 137.33, 32 plus, and 2.02 plus 171.35. That'll give us, divide that into this, that'll give us moles. 50.93, divide that into it. So I get 0.29, 4 places, 0.2972. Molar. All right. That's part 1. Part 2 takes a concentrated solution and dilutes it. Right? So we have the molarity of the concentrated solution, and we need a volume of that concentrated solution to give us the molarity of the diluted solution and the final volume of the diluted solution. So let's put their numbers in their proper place so that when we plug them in the formula, we don't put them in the wrong place. So what's the concentration of the concentrated solution? Is 0.2972 molar. What's the volume here? That's the question. How many milliliters of this solution must be diluted? So this one, and it's asking for milliliters. The molarity of the diluted solution needs to be 0.1. Okay? And the final volume needs to be a liter. Right. So remember, with this type of arrangement, we pick the volume ourselves. It's not restricted by the definition of molarity because it's a ratio. Right? We have MCVC equals MDVD. Right? So the volumes cancel each other. That means we can use any volume we want. I mean, we could use teaspoons if we wanted to. But if you put teaspoons in one, you're going to come out with teaspoons in the other. So let's change this one to 1,000 milliliters. Now our answer is going to be in milliliters. So this one is going to be 0.2972 molar. This one's going to be our answer. This one's going to be 0.100 molar and 1,000 milliliters. There we go. Now that's the hard part. The easy part is just crunching the numbers in your calculator. So we're going to leave this one here and put that one over there in the denominator. So this is going to be 0.1 times 1,000, which is 100. 1/10 of 1,000 is 100. And divided by 0.2972. So that's 336. Hold on a second. I may have made a mistake. Let's read the question again. How many milliliters of this solution must be diluted with water in order to make? Yeah, that's right. Let me check my calculations. Because if I'm right, then the answers there are wrong. But if that's right, then I made a mistake. So 50.93 grams, yeah. How about that one? Did I do that calculation right? Barium, 137.33. 2 oxygens, which is 32, and 2 hydrogens, 2.02. 171.35, that's right. Divide that into 50.93 is 0.2972, 0.1, and then that gives us this molarity. We need to know how much volume, how many milliliters of this solution must be diluted. Right, so that's the unknown. Final molarity is 0.1 molar. Yes, and 1 liter, which is 1,000 milliliters. Okay. So now, if we put them in 0.2972, that's no transposition error there. That's our unknown. 0.1 molar for this one, and 1,000 milliliters. Okay. So 0.1, enter 1,000 times. That was right the first time. Then divide by 0.2972. 0.2972. 336. Volume, 336 milliliters. So this one is wrong. That is an error. Let me make a note of that so I can fix it. So I don't want to use, I mean, if there's no answer in there, that's not fair to the student. Let's see. Correction. E equals 336. Okay. All right. Let's see. 49 is next on my list. 49. One. There we go. Okay. Excuse me. A 7.33 gram sample of lanthanum combines with oxygen to give 10.29 grams of the oxide. Calculate the empirical formula of this oxide. Okay, that looks worse than it really is. So let's put the information up here and get it away from the word problem. Right? I've always said word problems are meant to confuse. The information is there. It's just they try to confuse you. So 49. So we're given 7.33 gram sample of lanthanum. 7.33 gram of lanthanum. Okay. The oxide of the lanthanum is 10.29 grams. So lanthanum, and then whatever the oxide is, this could be, different subscripts, right? We don't know that yet. And they want to know the empirical formula. All right, the simplest whole number ratio of lanthanum to oxygen. All right, what do we know? Well, if this is lanthanum and this is the oxide, how much is oxygen? Oxygen's the difference, correct? 7.33 is 6, 9, 7 9 is 2. 2.96 grams of oxygen. Okay? So I'm thinking we know the mass here and the mass here. We just find out how many moles and then ratio them, correct? So this much lanthanum is how many moles? And this much oxygen is how many moles? So lanthanum, we just look it up. Let's see. Remember the group called lanthanides, right? They begin with lanthanum. So you go way down here, right there, right? So lanthanum, and then it kicks down here to this group right there. Those are the lanthanides. They start with lanthanum, which is 138.91. grams. So we divide that into 7.33. 7.33, enter. 138.91 divide. So you get 5.28 times 10 to the minus 2. Yeah. 5.28 times 10 to the minus 2 moles. Then this one, oxygen, of course, a single oxygen atom in this case is 16. So 16 into 2.96 is what? 1.85 times 10 to the minus 1. 1.85 times 10 to the minus 1 mole. All right. Remember how we get whole number ratios. The easiest way is to take the smallest one and divide it into everybody else. So which is the smallest one here? Well, the temptation is to do that one, but no. 10 to the minus 1, 10 to the minus 2. So we divide this one by that number and this one by that number. All right. So if we do that, we get 1, correct? And if we divide this one by 5.28 times 10 to the minus 2, right, we've already established the ratio of moles. Ratio of lanthanum to oxygen. That's established. So if we do the same thing to both of them, then we haven't changed that ratio. So let's see. I just need to invert that and divide. 3.5 rounded off. Okay. So we have an easier ratio to deal with, but it's still not a whole number. So how would you make that into a whole number? Just multiply by 2, right? 2 times 3.5 is 7, correct? Times 2 equals 7. Times 2 equals 2. So the ratio is lanthanum to oxygen 7. Okay? So it wasn't as difficult as it looked. It's just, it's best to put things up here on the board or on your paper in a way that makes more sense. And say, all right, this is what we're given. Does that tell us anything else? Well, yeah, it does. It tells you exactly how much oxygen you have. And then you can go to town on it. Let's see, I need another squirt of WD-40, I think. That's pretty good at cleaning the board too. Let's see, 55 is next on my list. 55. We're doing good on time. Okay, buffers. Let's talk buffers. 55. A buffered solution contains HNO2, right? In solution, what would that be? Well, it's got oxygen in it, so you don't say hydro. So you look at the anion of the compound, this NO2. What is that? Nitrite. Nitrites become ites become us's. So that's nitrous acid, HNO2. Okay? It also contains what? If it's a buffer, it has to contain the conjugate base. If that's the acid, it has to have the conjugate base. No two ways about it. So this is going to do what? Well, it's going to produce a proton. And remember what I said about protons. They're never out there independent like that. This is shorthand notation. So we consider the protons separately, although we know that they're really bound to a water molecule. But the stoichiometry is the same. So what do you have left over? You have NO2 minus. Okay? So that's required. Acid, conjugate base. Now, how do you get a conjugate base into this solution without putting it in as acid? If you put it in as acid, then this equilibrium is going to force everything to be over here because it's a weak acid. You need to get that into solution independent of the acid. So the way you do that is you find a soluble salt, something with that NO2, a spectator. And the best ones are the alkali metals. So you could do sodium or potassium, or it's a little more bit expensive, but lithium, even rubidium, nitrite. So which one do we have here? We have potassium nitrite. Right? So this one is going to be potassium. Okay? That's why KNO2 is the answer. You got to get that conjugate base right there. You got to get that in solution, independent of the acid. So also, you remember what I said about the ideal buffer? The ideal buffer is where this one is equal to that one in concentration. Okay, that was 55. I'm going to skip this one. I think I marked it out. 60. Okay. $60. I may need a little more room, so I'm going to start 60 over here. All right. A certain compound is found to have the percent composition: 85.63% carbon, 14.37% hydrogen. The molar mass of the compound is 42 grams per mole. What's the empirical and the molecular formula? Okay, so this is just step right through it from percent composition to the end. Right, you know how to do that. If we have carbon and hydrogen only, there's carbon, there's hydrogen, and the carbon is 85.63%. 85.63%. And 14.37%. And this is by mass. Okay? So how do we get around that percent? Remember, if you're given percent, you just assume that the sample is 100 grams. If the sample is 100 grams, then parts per 100 means 85.63 grams. Right? Assume 100 gram sample. 14.37 grams hydrogen. Now we've got something we can work with. And we bring in Henry Ford. Assembly line time. Okay, we need to convert from grams to moles. Grams to moles. So hydrogen is just 1.01 down here. Carbon is 12.01. Okay, so let's do some quick calculations there. 8563, 12.01 is 7.13. And 14.37 divided by 1.01 is 14.2. Okay. Now we could go ahead and divide this one by 7.13 and divide this one by 7.13, but I think you can eyeball it, right? What's the simplest whole number ratio here? 7 to 14 is 1 to 2. So the empirical formula is 1 carbon, 2 hydrogens. All right? So now we need to figure the molecular formula. That's the empirical formula. In order to do the molecular formula, you have to know the molecular weight, the molar mass of the compound. Right? Because this ratio is established. It didn't change. So we got to multiply the whole thing through by some value x. Right? Well, if the molar mass, the molecular weight, is equal to 42.00 grams per mole, then the multiplier would multiply by the mass, the empirical mass of this term would give us that term, and then x would be our multiplier. So what's carbon and hydrogen together? Well, let's see, carbon is 12.01, 2.02 for the hydrogens, 304, 14.03. Okay, so the empirical mass is 14.03 grams per mole. So the ratio of the two is what? Right? Let's see, 42 invert divide. Nearest whole number is 3. So this one divided by this one is equal to 3, approximately. And that's equal to x. So if this is equal to 3, then C3H6 is our molecular formula right there. Okay? That's how it's done. Okay, let's see, that was 66. 66. There we go. Okay, here's another one. All right, practice makes perfect. We're going to do another empirical molecular formula calculation. So I won't have to explain this one as much as I did the earlier one, because I'm going to do it exactly the same way. We're given a compound that contains 12.8% carbon. Okay, 2.1% hydrogen. And there's another one, bromine, 85.1% bromine. Oops. Bromine. 85.1%. All right. Assume 100 grams. Now we have 12.8 grams, 2.1 grams, and 85.1. So do our conversion. Carbon is 12.01. Hydrogen is 1.01. Bromine, I have to look it up. I know what chlorine is, but I don't use bromine that often. 79.90. 79.90. Okay. Now we'll do some calculating. Let's see, 12.8 divided by 12.01 is 1.07. Yeah, 1.066. Moles. 2.1 divided by 1.01 is 2.079. 2.079. These are all moles. And then 85.1 divided by 79.90. That's 1.065. 1.065. Moles. So we got a pattern developing here. We got one of these, and that's about the same. So that's 1 to 1, and that's 2. So it's approximately 1, 1, 2. So our empirical formula is CH2BR. We need to multiply it by some factor. So we need the molar mass of this one, right? We've got the things right here. We just say 12.01, and then 2 hydrogens would be 2.02, and then 79.9. 79.9 gives us 93.93 for this one. The empirical weight equals 93.93. The molecular weight is equal to what? It's given, 188. 188 grams per mole. So what's the ratio of this one to that one? Well, it looks like it's 2. But let's do it and find out. 188 and then divide by that other one. Yeah, 2.001. So X equals 2, and the molecular formula is C2H4Br2. Okay? If you do enough of these, you get pretty good at them. You just have to watch out for calculation errors and other types of mistakes. Because after all, the human brain is not a computer. Some computer scientists would like you to think that the human brain is a computer, but it's not. It can be used as a computer, but it's still subject to various types of errors. 78 is next. Here we go. There. This one looks familiar. I think we've done this one before, or one like it anyway. Let's do one again then. 78. All right. So we got a gas law problem here. This one, we better pull the information out and put it on the board. A flexible weather balloon contains helium at a volume of 855 liters. Initially, the balloon is at sea level, where the temperature is 25 degrees centigrade and pressure 0.947. This looks like a before and after. So the volume of the balloon before, the initial volume, equals 855 liters. And let's see, what else do we know? The balloon is at sea level, and the barometric pressure is 0.947. So the pressure at sea level is 0.947 0.947 atmospheres. And the temperature is 25 degrees. So the temperature is equal to 25 plus 273. Okay. All right. Now we let the balloon rise to an altitude of 5,500 feet. Right? Do we need to know that height? Not necessarily. We're given the information where the pressure is 0.785 atmospheres. Okay. And the temperature should have dropped to 15 degrees. Okay. And the question is, what is the change in volume of the balloon? So we can find out what V2 is, but the change in volume was how much difference is there between this one and that one. So we're actually saying V2 minus V1. But I'll tell you what, let's use some algebra. This one is going to be, what's going to happen to the volume as we go up? It's going to increase, correct? So this volume, this new volume, is equal to that volume plus a change in volume, isn't it? This way we can solve directly for that one because we know this one is 855. Okay, now let's plug it in the formula. We have P1V1 equals over T1 equals P2V2 over T2. And that V2 here is equal to P2 times 855 plus delta V over T2. Okay. Now, let's see. This one is 98, 298. Okay. And this one is 288K. So now, probably be easier just to plug in the numbers. So let's say, after I quench this phone, P1. Let's see, I probably ought to go over here, at least for part of it. Let's see. There. P1 is 0.947. And then V1 is 855. And then T1 is 298. And that's equal to P2, which is 0.785 times 855 plus delta V divided by T2, 288. Okay? So to solve this one, we want to get that term delta V on one side. So that means this one times these two divided by this one and divided by that one will give us this term right here. So 0.947 and 855 and then divided by 298, then multiplied by this one, 288, and divide by 0.785. So an intermediate equation says 855 plus delta V equals 997. And that's liters. So delta V equals 997 minus 855. So I get 142 liters was the change in volume. So that's 1.42 times 10 squared. There it is. 1.42 times 10 squared is 142. All right. That's 78. We got about 46 minutes left. And we might have to go to Thursday. So now we're into problem solving, and they take a lot longer. I mean, these more intricate problems. So that was 78. I marked it off. 79. Let's see what 79 has to say. A gas is collected over water at a certain temperature. The total pressure is 758 torr. The vapor pressure of water at this temperature is 17 torr. What's the partial pressure of the gas collected? Oh, this one's simpler than it looks. So what do you have? Well, you have a total pressure of 758. But that's a combination of two different pressures. Right? You got the pressure of the gas and the pressure of the water vapor. Right? We don't know the pressure of the gas, but we do know that the water vapor is contributing that much. So what does Dalton's law of partial pressure say? It says this one is equal to the pressure of the gas plus the pressure of the water vapor. So all we have to do is subtract this one from that one, and we get the pressure of the gas. $741 torr. Okay. That wasn't as bad as it initially looked, huh? We just have to know which law to use. Dalton's law of partial pressures. Let's see. Scoot that back a little bit. There we go. Let's see. What's next? 112. We got to scroll way down. Almost there. There we go. That's good. All right, 112. Oh, wait a minute. That's 113. There we go, 112. A solid object with a volume of 5.62 milliliters weighs 108 grams. Would this object float or sink in mercury? Okay. Right, so this is different. It's a similar concept. It's all based on Archimedes' principle. The lighter the density of the object, if it's less than the density of the fluid, then it floats. If it's greater than the density of the fluid, then it sinks. So that works for liquids. It works for gases too. That's why hot air balloons and helium balloons, blimps and dirigibles and whatever, that's why they float. Because overall, the density of that object is less than the density of the fluid. Okay, so 112, we have to calculate the density of the object. So mass per unit volume, right? 108 grams per 5.62 milliliters is equal to what? And then we'll compare it to the density of mercury. 108 and then 5.62. 19.2. 19.2 grams per milliliter. Right? That is greater than 13.6, correct? Greater than 13.6. So this thing is going to sink in mercury. There it is. All right. Let's see. Next, I got 115. 115 right here. Okay. A solution has a hydrogen ion concentration of 4.3. There it is again. Times 10 to the minus 8. That should be an X. Times 10 to the minus 8. 115. All right. So we're given hydrogen ion concentration is equal to 4.3 times 10 to the minus 8 molar. What they want to know is what's the pOH of this solution. So what's the quick way to do it without so much chance of getting the scientific notation wrong? Well, first thing you do is convert that to pH. Right? So negative log of this equals the pH. 4.3 exponent 8 minus, enter, and then do the log and change the sign. 7.37. Well, let's see. Is that right? Two significant figures means 2 decimal places. Yeah. 7.37. 7.37 pH. Now, what do we know? We know that pH plus pOH equals 14. So if we put 7.37 here, then we just subtract it from 14 and we get pOH. Well, I did something wrong. Let me try that again. There we go. 6.63 is the pOH. There it is right there. Now, let me answer the door. I got a crying kitty. You want to come in? Come on. Hurry up. No? What's the matter? Your brain too small? Come on in. Come on. Be cautious. Come on. Get in here. I got a class to teach. Make up his mind. Cat. The size of his brain is about the size of some bureaucrats I know. Not to name any names, of course. 115. 118. Yeah, we still got time. We can do 118. Here we go. Oh, this is just this is a kissing cousin to the last one we did. All right. If we know the OH concentration is equal to 5 times 10 to the minus 4 molar, then the negative log of that will give us pOH. .30. So the pH is equal to 14 minus 3.30. Uh, 10.7. Okay. Let me see. Two significant figures means 2 decimal places. 2 decimal. Oh, yeah, that's right. Should be 0. Yeah. 2 decimal places. All right, 118. $121. All right. A solution is prepared by dissolving 111.9 grams of hydrogen chloride gas in enough water to make 160 liters of solution. What's the pH? Okay, 121. What are we given? 111.9 grams of HCl. And the final volume is 160.0 liters. So if we're going to have to give this, determine the pH, what do we need to know? Well, we need to know the concentration of the hydrogen chloride in molarity. Then we need to know how much of that is hydrogen ions. Right? Well, we know that this is what happens. All of it goes. Right? It's a strong acid. So it produces the same concentration of hydrogen ions as hydrochloride, hydrogen chloride. So really all we need is the concentration here, and then we can calculate the pH from that. So we need moles here, correct? So chlorine is 3545 and hydrogen is 1.01. 35.45 and 1.01. So that's 3646. That'll give us the number of moles. I get 3.069. Okay, now we divide that by volume. 3.069 moles per 160.0 liters is 1.918. 1.918 times 10 to the minus 2 molar. So now what we have to do, since we know that this is 1:1, if we got this concentration there, we know it's that. So we just take the negative log of that value is our pH. And I get, let's see, 4 significant figures means 4 decimal places, 1.7171. They rounded it off. But the rules say you got 4 significant figures here, and I've been following it all along, then you can have 4 decimal places. Right? So there's another one. The best answer is 1.72, but technically none of these, because 1.7171 is not exactly the same as 1.72. Okay, we're coming up on 11:30. We go to 11:50, so I got 20 minutes. 133 is next. Here we go. Okay. A weak acid, HOCl. What's the name of that acid? Remember, I always start with ClO3. That's chlorate. So this is chloric acid. Right. This is chlorous acid, because that's chlorite. And this is hypochlorous acid. Okay. So now that we know what to call it, a weak acid, hypochlorous acid, is in solution with dissolved sodium hypochlorite. Right? So we've got, what is the controlling reaction here? What reaction are we talking about for this buffer? That's what they're describing, is a buffer, right? Because this one goes acid conjugate base, right? And this is our sodium hypochlorite. Well, sodium is a spectator, so we don't write it in. Okay. Now the question is, once we've established this, if hydrochloric acid is added, which ion will react with the extra hydrogen ions to keep the pH from changing? Well, if you're adding hydrogen ions here, that's going to be extra hydrogens, and Le Chatelier says they're going to react with this one and shift back to the left. So this is the answer. They're going to react with the conjugate base. Right? The proton acceptor is OCl minus. Let's see, 139. We squeeze a couple more in here. Yeah, 139. Aluminum oxide. Reacts with gaseous carbon monoxide to produce aluminum metal and carbon dioxide gas. Write the balanced equation. All right. So there it is. Right. And these R's here that are supposed to be registered trademark symbols, but that's supposed to be an arrow. So if we work from the problem itself, then we write aluminum oxide reacts with gaseous carbon monoxide. So aluminum oxide. This is -2 plus 3. So we need 3 of these and 2 of those. That's a solid. Plus gaseous carbon monoxide yields what? Well, it tells you. Aluminum metal plus carbon dioxide. So the first step is write your compounds correctly. If you can't do that, then you might as well just give it up. Okay, now we're going to balance the equation. So let's do our tally again. Aluminum, oxygen, carbon. So we got 2 aluminums, 4 oxygens, and 1 carbon. Now 1 aluminum, 2 oxygens, and 1 carbon. All right. What if, instead of focusing on this one to make it even, we focus on that one to make an even number? If we can get an even number of oxygens on this side, then anything we multiply this one's going to be even because there's a 2 there. Okay? So what if we, well, I don't know, what would make this even? Well, 1, it makes it even. but we want even at an elevated level. So if we multiply this one times 2, we still get an odd number. But if we multiply it by 3, now we've got 3 plus 3 is 6. All right. And now to get 6 over here, we need 3. So that's 6 oxygens and 3 carbons. Well, look there. 3 carbons here, 3 carbons there, 3 carbons here. And now we just need 2 aluminum. Okay? That was a little tricky. And the reason it is because you've got these 2 oxygen positions over here and only 1 over there. So that presents a problem. Okay, we might have time for one more. 147. An aqueous solution of potassium chloride is mixed with an aqueous solution of sodium nitrate. The complete ionic equation contains which of the following species when balanced in standard form? Sodium nitrate and potassium chloride. You know what? That's kind of stupid. Because when you put those in solution, they're not going to do anything. They're not going to react. I'll prove it to you. 147. Potassium chloride in solution combined with sodium nitrate in solution yields what? Well, if you swap them, you get sodium chloride, which is aqueous, and you get potassium nitrate, which is aqueous, right? So based on this reaction, they're all spectators. They're not doing anything. All right, let's try to answer the question anyway. The complete ionic equation, right? Let's balance it first. There's 1 potassium, 1 sodium, 1 nitrate, 1 chloride. It's balanced. So when you break it apart, what do you have? Well, you have this one, you have this one, you have this one, and you have this one on that side in aqueous solution. Same for the other side. So which species does it contain? Well, these prefixes, 2, 3, 2, 2, none of those there. They're all 1 to 1 to 1 to 1 to 1. So chloride is the only thing that matches right here. It's on both sides, actually. That's really not a reaction. There's no reaction going on there. You just mixed up a solution of potassium chloride and sodium nitrate. Now, if this had been silver nitrate, that's a different story. Oh, I forgot to put the number, 147. If this were silver nitrate right here, then you would have that's definitely a reaction because silver chloride is insoluble. So silver nitrate, silver swaps places with potassium, makes a solid. And you still got the same answer. You still got chloride ions on this side. Okay. I bet that's what was meant to be done, but they didn't do it. So let me check 147. 147. Yeah, check it later. All right. So let me see. I've got to jump down to 172 but we're getting close. Maybe this would be a good place to break. Let me check it. 72. 72. Yeah, now we're getting into electrochemical cells. This would be a good break point. So I'm going to mark that here. Mark here, and we'll pick it up on the 6th of May. And finish out our review. Okay. That's part 1.